Assalamualaikum and good day everyone. This lecture video is about chapter 13, Intermolecular Forces. So this is the learning outcome for this chapter. You should be able to explain two types of intermolecular attraction, van der Waals forces, which it has two types, dipole-dipole interaction and London dispersion forces. And the other type of intermolecular attraction is hydrogen bonding. Learning outcome number 2 is to explain factors that influence van der Waals forces and hydrogen bonds. Next, relate the effect of van der Waals forces between molecules on the following physical properties: boiling point and solubility. Lastly, relate the effect of hydrogen bonding on the following physical properties, which are boiling point, solubility, density of water compared to ice. Now let's look at the introduction of the intermolecular forces. What is intermolecular forces? So these forces are the force that occur between molecules, whereas intramolecular forces are those within molecules. So for example, intramolecular forces is covalent bond, ionic bond, that is intramolecular forces, the interaction within molecules, meaning that in the molecules. For example, as you can see the figure below, the interaction between hydrogen and chlorine, which is a covalent bond, this is intramolecular forces. So intermolecular forces is force between molecules. So between this HCl molecules, we have interaction. So this interaction we call as intermolecular forces. So intermolecular forces are much weaker than the intramolecular forces, but however, it has more influence in the state of matter, gas, liquid, and solid. So intermolecular forces has effect on the physical properties of boiling, melting, and solubility. So let's look at the type of intermolecular forces. The first one is about van der Waals forces. So intermolecular forces or van der Waals forces are attraction or repulsion forces between neighboring atom, molecules or ion, and very much related to physical properties, a boiling point, melting point, and so on. There are two types of van der Waals forces, which are the first one, dipole-dipole interaction, or known as the permanent dipole force, and number two is London dispersion forces. So for example, HCl molecules just now, it has the permanent dipole forces. Another example for London dispersion forces is about it's like chlorine molecules. So the interaction between chlorine molecules. So here is London dispersion forces. So let's look more about dipole-dipole interaction. So this occurs when there is a large difference in electronegativity between atoms which is bonded together. For example, HCl. So there are different electronegativity between hydrogen and chlorine, which is chlorine is more electronegative. So this will cause the shared pair electron to be distributed unequally, meaning that the shared pair electron is distributed unequally. The chlorine atom attract electron towards itself. Okay, make the chlorine atom become electronegative, partially electronegative, and the hydrogen become partially positive atom. So the electron are pulled towards the more electronegative atom, and they are much weaker than ionic or covalent bond and have a significant effect only when the molecules involved are close together. Okay, so in some solution, for example, hydrochloric acid solution, so there are many HCl molecules. So all the HCl molecules, okay, the chlorine will attract the electron here toward itself, make the chlorine become partially negative, and the hydrogen partially negative. So this partially positive, sorry. So this chlorine and this hydrogen will attract. Okay. So this attraction we call as a dipole-dipole interaction. So the strength of the dipole-dipole interaction depends on the size of the dipole moment of the connected molecules. And the higher the dipole moment, the stronger the dipole-dipole attraction, thus making the substance will be more polar. So dipole moment is actually a quantitative measurements that describe two opposite charge separated by a distance. That is dipole moment. The bigger the dipole moment, okay, make the bond more polar, and the strength of the dipole-dipole interaction will increase. So this is the dipole-dipole interaction in HCl molecule. So here the dipole-dipole interaction between the molecules lah. Okay. Now let's look at the London dispersion forces. So the London dispersion forces is the weakest intermolecular forces. Non-polar atom and molecules experience London dispersion forces due to the motion of electron. These forces occur between atoms or molecules of non-polar substance which do not have permanent dipole. So atom or molecules that no permanent dipoles, it will have London dispersion forces. So atoms or molecules which have no permanent dipole are usually from the monoatomic atom, which is the noble gas of helium, neon, argon, krypton, and xenon, or diatomic molecules such as hydrogen, nitrogen, oxygen gas, fluorine, and chlorine, and the non-polar compound which have symmetrical electron distribution, for example, methane, and so on. So the non-polar molecules only have this London dispersion forces as the attractive force to sustain the attraction between molecules. So the London dispersion forces could occur in two different attraction, which is the temporary or instantaneous dipole and induced dipole. Okay, so let's look how London dispersion forces occur. So this is helium, okay, electron, the instantaneous uneven distribution of electron in helium, because we know that the electron is moving, okay, around the nucleus. So when electron move to one side, okay, both electron move to one side, okay, this is called, we call as instantaneous uneven distribution. So this side will become partially negative and this side will become partially positive. So this is non-polar helium atom, meaning that the distribution of electron is even. Okay, so when one of the helium atom has instantaneous uneven distribution of electron, it will affect, okay, it will affect this non-polar helium atom. So this is partially positive. So electrons more likely to move this side. Okay, so this side will become partially positive. So this is we call as induced dipole on neighboring helium atom, resultant attractive force. So when this side become electronegative and the other atom and this side become partially positive, so it will attract to each other. So this attraction or this interaction we call as London dispersion forces. Okay, now let's look at the factor that influence van der Waals forces. First factor is molar mass or molecular weight. So higher molar mass molecule will have higher boiling and melting point. Why? So as the molecule get bigger, more moving electrons are around, causing stronger London dispersion forces and intermolecular attraction to increase. Thus, more heat energy is needed to turn them into either a liquid or gas, resulting to higher melting and boiling point. So as we can see the example below, from methane to pentane, so the molecular weight of these molecules or this substance is increasing. Okay, so the boiling point also increasing. And then next is the second factor that affect the van der Waals forces is the shape of molecules. So the shape of molecules are related to the contact surface area. Larger contact area will result to higher London dispersion forces, stronger van der Waals forces, thus making the boiling point higher. Okay, for example, pentane to methylbutane to dimethylpropane, both of these structure has same molecular weight, okay, or molar mass. But the shape of this structure is different. We call as isomer. Later we will look this about isomer in next semester. Okay, so still pentane to methylbutane, still it has five carbon with 12 hydrogen, but the position, the shape is different. So as we can see, N-pentane, the boiling point is 36, but when we have branch here, 2-methylbutane, we call as a branch, so the boiling point is decreasing. Okay, and then when we have two branch, the boiling point is decreasing. This is because the surface or the contact surface area become smaller. So the interaction between molecules and molecules becomes weaker. That is why the boiling point is lower when the shape of the molecules becomes smaller. Okay, that's about van der Waals forces and the factor that affecting the strength of the van der Waals force. Now, let's look at the hydrogen bonding. So, hydrogen bonding is a type of intermolecular forces of attraction between a hydrogen atom that bonded to a highly electronegative atom, fluorine, oxygen, and nitrogen, and a highly electronegative atom of another molecules. Okay, so that is hydrogen bonding. For example, molecules that contain hydrogen bonding is water molecules. So the partial positive charge on the hydrogen atom will then be attracted to the lone pair electron on another highly electronegative atom of the neighboring molecules. So hydrogen bonds are highly polar, and the most electronegative atom, which is fluorine, when bonded to hydrogen will exhibit the strongest bond when compared to oxygen and nitrogen. Okay, so hydrogen bonding, when hydrogen bond with fluorine is more stronger compared to when hydrogen bond to oxygen and nitrogen. This is because of the electronegativity of fluorine is higher compared to oxygen and nitrogen. So this is the example of hydrogen bonding. So the interaction between oxygen and hydrogen, here we call as hydrogen bonding. But the interaction between carbon and oxygen is a dipole-dipole interaction. So at the right side, you can see another example, the interaction of the hydrogen bonding. So this is water molecules, hydrogen bonded to the oxygen, and then the interaction of this oxygen with hydrogen from another water molecules we call as hydrogen bonding. So you can see lah, another example here is the hydrogen bonding. So factor that influence hydrogen bonding. So the factor is the strength of the hydrogen bond depends on the electronegativity of the fluorine, oxygen, and nitrogen atoms. Higher electronegativity resulted to stronger hydrogen bond. For example, hydrogen bonding occur in both HF, hydrogen fluoride, and H2O. F is more electronegative than oxygen. However, H2O can form 4 hydrogen bonding with other water molecules, unlike hydrogen fluoride only form 2 hydrogen bonding with other hydrogen fluoride molecules. So even though the HF is much more electronegative, but HF have boiling point when compared to water molecules due to multiple hydrogen bonding in water. Okay, so hydrogen bond between interaction hydrogen and oxygen. Okay, interaction between hydrogen and oxygen compared to interaction hydrogen dengan with fluorine. So the interaction between hydrogen with fluorine is more stronger compared to the interaction of hydrogen and oxygen. But for example, in water molecules and HF, so water molecules has higher boiling point because of water molecules can make 4 hydrogen bonding. Meanwhile, the hydrogen fluoride can only make 2 hydrogen bond. So you can see the figure below about the interaction in water molecules and hydrogen fluorine. So this is the hydrogen bond. Okay, so here. So fluorine, hydrogen fluoride, it only can make 2 hydrogen bond only. So this is as a conclusion about the intermolecular forces. So we have London dispersion forces, dipole-dipole forces, and hydrogen bonding. So definition, London dispersion forces, attraction between two instantaneous dipole, asymmetrical electron distribution. It occurs at all atoms and molecules. So all the atom and all molecules will have London dispersion forces, meaning that in water molecules, we also have London dispersion forces, even though the strongest forces in water molecules is hydrogen bonding. But still in water molecule, it has London dispersion forces because of hydrogen can interact with hydrogen in water molecules. So here is the example of London dispersion forces between hydrogen gas. The strength is the weakest, increase in strength as molar mass increase. And then we look at dipole-dipole forces, attraction between two permanent dipoles, and it occurs in a polar molecules, for example, HCl. So the interaction between hydrogen and the chlorine atom is a dipole-dipole interaction. So it has medium strength, stronger when molecules are closer together or when the dipole moment increase, the dipole interaction forces strength also increase. And lastly, hydrogen bonding is attraction between molecules with NH, OH, or FH bonds, extremely polar bonds, very strong dipole-dipole forces. For example, is in water molecules. So the relative strength is the strongest. And remember, hydrogen bonding is not a chemical bonding. Okay, it's not like covalent bond, ionic bond. Okay, hydrogen bonding is intermolecular forces. Now, let's look at the effect of intermolecular forces on physical properties. First, we look at the boiling point. So the nonpolar molecules relies on the London dispersion forces to maintain the interaction between molecules. The more electron and the bigger size the molecule have, the greater the London forces are and the higher boiling point will be. So example, tetrahedral in group 14. Okay, so as we go down this group, so the size of the molecules becomes bigger, the molar mass increase. So when the size of the molecules become bigger, so the interaction between the molecules becomes more stronger. So we need more energy to break the interaction between molecules and molecules. So that's why the boiling point is increasing. Let's look at the example of boiling point of water, hydrogen sulfide, hydrogen selenide, and hydrogen telluride. So among these compounds, water has the highest boiling point due to the hydrogen bond. So other than H2O, all the molecules are non-polar, which only have London dispersion forces. As the size of molecule increase, the strength of the London dispersion forces increases and the boiling point will be increased. So if you need to arrange this boiling point of these molecules between water, hydrogen sulfide, hydrogen selenide, and hydrogen telluride, so the lower boiling point is H2S, hydrogen sulfide. Okay, hydrogen sulfide followed by hydrogen selenide, hydrogen telluride, and water molecules. The water molecule has the higher boiling point because of the intermolecular forces in water molecules is hydrogen bonding, which is the strongest intermolecular forces. That is why water molecules have higher boiling point. So between these three molecules, it only has London dispersion forces. So this is increasing because of the size of these molecules is increasing. So that's why the boiling point increase. Another example of boiling point of diatomic molecules, for example, fluorine, chlorine, bromine, and iodine. So this is diatomic molecule. So between the individual molecules exists a London dispersion forces which are relatively weak when compared to dipole interaction. So the melting and boiling point of halogen are low because of the interaction is only London dispersion, which is the weakest interaction. That's why the boiling and melting point are low. So the increasing in the boiling point down the group is due to the size of the molecules increasing, making the London dispersion forces become stronger. So when the London dispersion forces become more stronger, so we need more energy to break the interaction. That is why the boiling point increasing. So you can see in the table below the melting point of the boiling point of group 17. Okay, going down the group 17, the melting point and the boiling point is increasing due to the stronger London dispersion forces. Next, we look at the solubility. So the dissolving solute must be able to break up the aggregation of molecules in the solvent. The molecules in the solvent must have sufficient attraction for the solute particle to be removed, meaning that it must contain the same attraction between solvent and solute to make the solute dissolve in the solvent. So type of bond, substance, okay, for example, water, type of bond, ionic bond, substance. Example of substance is sodium chloride. So sodium chloride is very soluble in water molecules because of water has sufficient attraction to remove the solute particle, okay, to separate the solute particle. So when sodium chloride dissolves in alcohol, it is slightly soluble, but when it dissolves in benzene, in a non-polar solvent, is insoluble. Okay, because of this solvent, it does not have sufficient attraction to break the attraction between sodium chloride molecules. We look at the polar covalent substance, which is sucrose. Okay, sucrose is a polar covalent molecules. Okay, when dissolved in water, which is a strong polar covalent solvent, okay, it is a very soluble. But when dissolved in alcohol, it also soluble. When dissolved in non-polar solvent, it is insoluble. Next example for non-polar covalent bond, naphthalene. It is very insoluble in water due to the molecular forces in naphthalene is because of naphthalene is non-polar, so it cannot dissolve in polar solvent because of it does not have the sufficient attraction to remove the molecules between molecules. And then solubility of naphthalene in alcohol is soluble, but when we dissolve naphthalene in benzene, very soluble. So let's look at the solubility of sodium chloride in water. Cation and an ion. Okay, cation, sodium plus, and an ion, chloride, Cl minus. In NaCl crystal are only attracted to each other via the ion dipole interaction. So the water molecules are hydrogen bonded to each other. So when NaCl is placed in water, it will dissociate to Na plus and Cl minus. So the negative fluoride ion on the surface are attracted by partially positive hydrogen atom in the polar water molecules. So that interaction we call as ion dipole interaction. So positive sodium ion are attracted by the partially negative oxygen atom in the polar water molecules. So we can see at the right side the figure. Okay, so this is crystal NaCl, meaning that in a solid form. So when you dissolve in water, when you put this NaCl in water, it will dissociate to Na plus and Cl minus. So this ion, it will interact with water molecule. So water molecule, sodium plus, it will attracted with the oxygen atom in water molecules. Since oxygen atom now is partially negative atom. Okay, and then the chloride ion, it will attracted by the partially positive hydrogen atom. So this interaction between the chloride ion and water molecules we call as ion dipole interaction. Several water molecules are attracted to each of the ions. So once the ions are released from the crystal, the ions are completely surrounded by a water molecule, and this process is called solvation. And solvation is an exothermic process where heat is generated to overcome the lattice energy that holds ion in a crystal. Now let's look at the solubility of ethanol in water. So each alcohol consists of a carbon chain, always non-polar, and OH group, which is polar. So ethanol has chemical formula C2H5OH, and ethanol has two carbon chain and OH group. As water is polar, it's attract OH group for hydrogen bonding. So this is the structure of ethanol. So it has two carbon chain and OH. So this side, water molecules will attracted to this side and make hydrogen bonding. So the carbon chain on the other hand, as non-polar, is repel. So, but due to the attraction strength of the OH group, first three alcohol, methanol, ethanol, and propanol, are completely miscible, meaning that completely soluble to dissolve in water in any amount. Starting the 4-carbon butanol, the solubility of alcohol is starting to decrease after the 7 carbon heptanol alcohol are considered immiscible, cannot be dissolved in water. Okay, so the longer the carbon change when you dissolve in water, it cannot, it immiscible. Okay, due to their hydrophobic area becomes larger. Okay, let's look next. Let's look at the solubility of ammonia in water. So ammonia has the ability to form hydrogen bond. When the hydrogen bond between water molecules are broken, they can be replaced by equivalent bond between water and ammonia molecules. So that is why ammonia can be dissolved in water, because of ammonia can make hydrogen bond between water molecules. And last, solubility of nonpolar compound. So phosphorus P4 is a nonpolar molecule and does not dissolve in polar solvent such as H2O. Why? By using the light dissolve light principle, P4 need to be dissolved in nonpolar solvent, and it was found that uh, it can be dissolved in calcium, carbon disulfide. Okay, because of P4 phosphorus readily dissolve in carbon disulfide because the intermolecular process that are broken in both solute and solvent are very similar to the intermolecular process that are formed between the solute and the solvent molecules. So when we look about solubility, we must use the principle light dissolve light, meaning that polar molecules only can be dissolved in a polar solvent. Meanwhile, non-polar compound or non-polar molecules can be dissolved in non-polar solvent. H2O shows no interaction with phosphorus, and this because both phosphorus and H2O are not strong enough to compensate the broken hydrogen bond in H2O and London dispersion process in P4. That's why phosphorus is not dissolved in water. So if the attraction are sufficiently different, the strong attracted molecules will cling together, excluding the weakly attracted molecule, and immiscibility will result. So relatively different intermolecular process strength does not support the process of solubility in both polar and non-polar compounds. Now let's look at the density of water compared to ice. So water is one of the few substances that is less dense as a solid ice than its liquid. So when you go to a restaurant and you order ice kosong, so the ice is floating in the water on top of the water. Okay, because of the ice is less than the liquid, but the molecule still the same, which is H2O. So why this is happen? Okay, this is because water in the form of ice has an open hexagonal structure, whereas liquid water does not. Water molecules arrange themselves in such a way as to maximize a relative large amount of space between them and give rise to an open structure. When ice melt, some of the hydrogen bonds are broken. Okay, so this allows the water molecules to be more complexly arranged. Therefore, water has higher density than ice. So when you have ice, so ice in form of solid, meaning that the molecules of water here is not moving and it has an open hexagonal structure. The volume of the when it has open hexagonal structure, the volume will be increasing. So density is equals to mass over volume. So when the volume is increased but the mass still the same, the density will becomes lower. So that is why the density of ice is lower compared to the density of water. Okay, further explanation. So this is due to the ice structure which has a rather open lattice, making the density is less at its freezing point than that of liquid water. The structure of liquid water is changing from that of ice to the short range structure of the liquid. So liquid water is of course also highly hydrogen bonding, but the extra energy it contains means that its structure is far less regular, then becomes slightly denser than ice. As the water molecule can move about more in the liquid than in the ice, the hydrogen bond will bend a little or break as molecule rotate. So this will lead to a shorter bond distance and hence slightly higher density in liquid than in the solid. So this is the the crystal structure of ice. So this is the exercise, so you can try to answer this question. And that is all for chapter 13. Thank you.